So question number 1 from the paper says, a solid cylinder of weight 24 Newton is made of a material of density 850 kilograms per meter cube. The cylinder has a length of 0.18 meters as shown in figure 1.1. Show that the cross-sectional area A of the cylinder is 0.016 meters squared. So they've given you the weight, they've given you the density, they've given you the length. They want you to calculate the area. Now, what formula do you use? You start off with the formula that includes area, and that is volume is equals to cross-sectional area times the length. Now, if you talk about the density of a solid, density is mass per unit volume. And mass, as we all know, because we are not given the mass, instead we are given the weight of the container. Yes, this is paper 23. What we'll use is, we'll use density is equals to mass, which can be replaced with M is equals to W upon G. So W divided by G times A times length. I've replaced volume with area into length. I've replaced mass with W upon G. And all you need to do next is plug in the values, make area the subject of the equation, and solve for A. So the density of the cylinder is 850. The weight is 24 divided by G, which has a value of 9.81, times the cross-section area, which is an unknown, times the length, which is 0.18. Make A the subject of the equation. What do you get? You get the answer as A is equals to 0.01599, which is equals to 0.016, and that is what they wanted you to show. Part B of the question says, the cylinder in A is attached by a spring to the bottom of a rigid container of a liquid as shown. The cylinder is in equilibrium with its bottom face at a depth of 0.17 meters below the surface of the liquid. The tension in the spring is 8 newtons. Show that the upthrust acting on the cylinder due to the liquid is 32 newtons. Show that the upthrust is equals to 32 newtons. Now, how do we solve this? We're given two, as far as the forces are, it's a 1-mark question, so it has to be straightforward. They don't expect a lot of calculations in this case. So what are the forces that are given to us? They've told us that there's a downward force, weight of this container. And that is equals to 24 newtons. Along with that, they've told you that there's a tension in the spring. And the tension in the spring is 8 newtons. These are the two forces. Now, even if you're stuck here, you can see that these two forces, when you add them up, they give you 32 newtons. Where will the direction of the tension be acting? Now, tension in the spring causes the cylinder to be downwards. The same tension causes a downward 8 Newton force. And for the base, the base experiences an upward force. So as we discussed earlier in class, tension, the direction of tension depends on your subject. So the subject here is our cylinder. So for the cylinder, if I ask you, can you mark down the forces? The forces on the cylinder are, there's a 24 Newton force downward, which is the weight of the container, or weight of the cylinder. There's a tension in the spring that basically pulls it downwards, 8 Newtons. And the cylinder, according to the question, is in equilibrium, which means that the downward force, is equal to the upward force. So the upward force, if it's balanced, should be equal to the sum of the two. And the upward force, the only upward force that can act on the cylinder is the upthrust in this case. So upthrust is equals to 24 plus 8, which is equals to 32 newtons. Isn't it supposed to be acting in the opposite direction to the weight? No. It should not be acting in the opposite direction to the weight. That's a misconception. If this cylinder was instead hung from the top using a spring, then the tension would act in the opposite direction to the weight. The weight would be downward, the tension would be upward. And in that case, if it's an equilibrium, the weight would be equal to tension. Or even if it was submerged in water, I'd still say the weight is downward, the tension is upwards, and then there's an upthrust force. So tension plus upthrust, the two upward forces, those are equal to the weight. I'd say that. If there's tension in the spring has a tendency to return back to its normal position. And that causes the spring to apply a downward force. And that is the downward force. It's like if I ask you, what would happen if you pull a spring upwards? There'll be tension in the spring. That tension would basically pull you downwards. Afnan, is that clear? Do you get the direction? Ibrahim, remind me to answer your question. I've got a comment on that. I'll do it at the end. No, I won't do it in the next class. Remind me at the end of the class. So moving on to part 2, calculate the density of the liquid. What is the density of the liquid given that you have the upthrust? Now, delta P is equals to rho GH. Delta P is equals to rho GH. We don't have the change in pressure. We do have the upthrust. Upthrust is a force. So force is pressure times area. So can I say upthrust is equals to rho GH times the area? Yes, I can. All I need to do next is plug in the values. Do we have the upthrust? Yes, we do. Upthrust is equal to 32. Do we have the density of the liquid? No, we don't. That's what they want us to find out. Do we have the value of G, 9.81? Do we have the height of the container? Yes, we have the height of the container. It's 0.17 given in the question. Do we have the cross-sectional area? We found that out in the first part. It's 0.016 meters squared into 0.016. And that gives you the density rho of the liquid. Rho is equals to 1200 kilograms per meter cube. Approximately, rounded off to two significant figure, it's 1200 kilograms per meter cube. That's the density. Or you could have found out using the upthrust and the cross-sectional area, you could have found out the pressure first and substituted it in this equation, and then use that to calculate density. That would obviously result in the same thing. I've combined the two equations and made one equation. Part C says, figure 1.3 shows the variation of the tension F with the length L of the spring in B. How does the tension in the spring change as the length changes? So the tension increases 30 centimeters onwards. The tap at the bottom of a container is opened so that a fixed amount of liquid flows out of the container. So you have a tap at the bottom. They've opened that tap, and that basically causes liquid to flow out. The cylinder moves downward so that the tension in the spring changes from 8 newtons. So the tension changes from this value, 8 newtons, to 4 newtons. Determine the change in elastic potential energy. What is the change in elastic potential energy? When they ask you for the change in elastic potential energy, if you have a force extension graph, you can use the area under the force extension graph to calculate the change in elastic potential energy. That would result in the right answer. You don't have a force extension graph. You have a force length graph as opposed to a force extension graph. So you can either modify this graph to you can modify this graph to convert it into a force extension graph. Because I believe, I don't know if they've mentioned it here. They haven't. So this 30 centimeters is the natural length. So at 30 centimeter, the extension is 0. I'm plotting the extensions below the length. At 10 at 40 centimeters, the extension is 10. At 50 centimeters, it's 20, 30, 40. Now I can use the area under the graph. And it's not a triangle. What I need to do is, this here is the area from 6 to 4. Let's shade this area. This is what I'm talking about. You can find out the area under the graph. Make sure you convert centimeters into meters, and that would give you the elastic change in elastic potential energy. Change in elastic potential energy is equals to half into, because it's a trapezium, half into height into sum of parallel side. This part here is the height from this point up till this point, which is equals to 20 centimeters. So 20 upon 100 times sum of parallel side. What are the parallel sides? One of the side is 4, the other side is 6. The other side is 8, sorry, not 6. 4 plus 8. So the answer that you get is 1.2 joules. Or if you want to avoid this altogether, you can use half fx or half kx squared. Find out the energy at 8, find out the energy at 4 using any of these formulas, and then find the difference. So how did you get 10, 20, and 30? Seher, what I did here is that I used 30 centimeters, the original length, even though in this question you don't need to, but this is a conceptual thing. I wanted you to understand this, that when you're finding out the area under the graph, the area under a force extension graph gives you energy. This is a force length graph. So 30 centimeter is the natural length, because when the force is 0, the length is 30. So this is extension is equal to 0. At 40 centimeter, the extension would obviously be 10, and then 20, and then 30, and then 40. That's how I got 10, 20, 30, 40. There's another question. If it's asking for elastic potential energy, why can't we use force into distance? The problem with that, Afnan, in a lot of cases, when we use work done is force into distance, I get your point. The force should be constant. You can only use W is equal to F into D when you've got the average force or you've got a constant force. The force in this case is not constant. That is why you cannot use half into, you cannot use force into distance. But what we've done here is, even though you may not have realized it, but Afnan, what we've done here is, when we found out this thing, 4 plus 8 multiplied by half, which gives you 6, we have found out the average force. 8 और 4 का average क्या होगा? 6 होगा. तो basically force into distance ही किया है हमने, लेकिन average force find करके, without you realizing that this is what we did. Is this clear? Best. Seher, do you get it? So 1.2 joules. So one more thing. I want you to understand, please, please, please do not make this mistake. A lot of students, when using half kx squared, what they do is they say half k x2 minus x1 squared, which is incorrect. You cannot write it like this. You'll have to write it as half k x2 squared minus half k x1 squared, or you can write it as half k x2 squared minus x1 squared. A minus b whole squared is not equal to a squared minus b squared. Don't make that mistake. If you're unsure, do it separately. Yes, a lot of students do that. Please don't do that. Especially, and the problem would only be when you have squares. If you use half fx, then you won't have a problem with this. More liquid is let out of the container until the upthrust on the cylinder becomes 24 newtons. For the upthrust of 24 newtons, determine the length of the spring. For the upthrust of 24 newtons, what is the length of the spring? Now, going back, what is the weight? What is the weight? The weight of the cylinder is 24 newtons. So let me get rid of this. The downward force weight of the cylinder is 24 newtons at some instant after we let a lot of water run out. The upthrust is also 24 newtons and it's in equilibrium. Now, if I ask you, what is the tension in the spring? Given that the upward force is 24, downward force is 24, what is the downward force exerted by the spring? There is no downward force. There is no tension because W is equals to upthrust. So T should be 0. If the tension is 0, if the force is 0, what will be the length of the spring? The length of the spring will be 30 centimeters. The spring experiences no tension. Hence, it will be at its original length, unextended length. Moving on, question number 2. State what is meant by work done. Work done is the product of force and displacement in the direction of that force, or the distance moved in the direction of that force. Use your answer in A to show that the SI base units of energy are kilogram meter squared per second squared. Work done, force times displacement. Force is measured in newtons. You may either say that force is mass times acceleration times distance, or you may not feel the need to write that out, which is equals to kilogram meters per second squared times the distance, which is meters, which is equals to kilogram meter squared per second squared. So you may skip this step of writing force as M times A and write it directly as kilogram meters per second squared, or you may write this, your call. A metal rod is heated at one end so that the thermal energy flows to the other end. The thermal energy E that flows through the rod in time T is given by E is equals to CA, T1 minus T2, T upon L, where A is the cross-sectional area of the rod. T1 and T2 are the temperatures of the ends of the rod. L is the length of the rod. C is a constant. Determine the SI base units of C. Now this is simple. We need to determine the SI base units of C. We've got the SI base units of everything else. So you may either make C this, but I'd prefer making C the subject of the equations first, and then substituting the unit. That reduces the chances of error. If you substitute the units first and then shift them around, that may result in some error. So C is equals to E times L upon A, T1 minus T2 into T. And once you've done that, just plug in the units. Energy is kilogram meter squared per second squared. Length is measured in meters upon area, which is measured in meter squared. T1 minus T2. T1 is measured in Kelvin, T2 is measured in Kelvin. So T1 minus T2 would also give you Kelvin. You can either write it as K minus K, Kelvin minus Kelvin, as long as you don't make the mistake of canceling these two out. They don't cancel out. Kelvin minus Kelvin would give you Kelvin, because we're talking about the units here. If there's a problem with that, ask right now. So you get Kelvin over here times T, a lowercase t, which is time. So second. Simplify and get the units for C. Meter squared here cancels out with meter squared in the denominator. This meter squared cancels out with this meter squared. And then you need to shift everything to the numerator and simplify. So kilogram, meters, you shift this second to the numerator. This becomes s to the power minus 1. Minus 2 plus minus 1 is equals to minus 3. So s to the power minus 3. You shift this k to the numerator, you get k to the power minus 1, k to the power minus 1. So kilogram, meters per second cube per Kelvin. These are the units for C. Yes. That's question number 2. Question number 3, a question on kinematics. Define velocity. You may either write it's a change in displacement per unit time, or you may write rate of change of displacement with respect to time. Basically mean the same thing. Part B says, a remote controlled toy aircraft is flying horizontally in a wind. Figure 3.1 shows the velocity vectors to scale of the wind and of the aircraft in still air. So the diagram here is made to scale. The velocity of the aircraft in still air is 42 meters per second to the north. The velocity of the wind is 23 meters per second in the direction of 54 degrees east of south. Determine the magnitude of the resultant velocity of the aircraft. So they want you to determine the magnitude of the resultant velocity of the aircraft. Now, there are two approaches to this question. Because they've told you that the diagram here is drawn to scale, you may either use that scale and get an answer. That's one way to do it. Or you may solve it mathematically, and that would also result in the correct answer. So if you were to draw it, if you were to solve it by drawing it to scale, you would first need to measure this length out, 23 meters per second. You'd also have to use the head to tail rule. So let me zoom in. This here is our vector. Or you may use the cosine law if you know how to do it. You've got both options. So this here is our vector. When using the head to tail rule, the tail of one vector is attached to the head of the other vector. So I'll attach this over here. There we go. And then what I'll have to do is I'll have to draw the resultant. My resultant starts from this point all the way up till this point. This here is my resultant velocity R. Now, why did I draw it like this? Obviously the head to tail rule, or you can think of it this way. The aircraft flies straight if there is no air. But if there's air blowing in this direction, that would obviously steer the aircraft to the right. That would obviously deviate the aircraft, the path of the aircraft to the right. So the resultant is in this direction. If you have a ruler, let me see if I have one. Just a second. Here we go. So I've got a ruler here. Obviously, it's not to scale. You'll get a different scale. I can enlarge this ruler. You cannot do that. So your ruler would have a fixed length. Use that ruler to come up at which angle will we draw the resultant. You don't need to figure out the angle for the resultant. What you need to do is you need to draw this wind velocity, the green vector that we've drawn here, at an angle of 54 degrees. Opposite angle, vertically opposite angle, right? If you draw this to 54 degrees, and you need to draw this, the length of this vector should be of the same length as this one. Once you've drawn this, for the resultant, you just need to connect the two. Is there any mathematical way to solve this? Yes, there is. We'll talk about that. So I want you to understand this method first, in case they ever ask you to solve it using a scale diagram. So what you may do is, what I feel here is that if I put it somewhere over here, I realize that this vector has a length of approximately 7 centimeters. And this 7 centimeter represents 42 meters per second. This is what I think. You'll get a different value. Once again, let me tell you that this is not a real ruler. It does not have a fixed length. So 7 centimeter represents 42 milliseconds. 42 meters per second, my bad. What you need to do next is you and find out the length of this vector here. This vector has a length of approximately 5.5 centimeters. Use this 5.5 centimeters is x meters per second. Cross multiply, get an answer. What answer do we get? 42 times 5.5 divided by 7. The answer that I'm getting is 33 meters per second. Exactly 33 meters per second. So that's my answer using the head to tail rule. X is equals to 33 meters per second using a scale diagram. Is this clear? Do you get this technique? Talking about the mathematical way of solving this, once you've drawn this out, even if you've not drawn it to scale, even if you've drawn it using a free hand, you know that this is 42, this here is 42, this here is 23, and this here is 54. Use the cosine law. What is the cosine law? The cosine law says a squared is equals to b squared plus c squared minus 2bc cos a. Now, these lowercase a, b, and c are the lengths, and this uppercase A is the angle. So A is this length, and this capital A is the angle in front of the length. And then plug in the values. R squared, this is the resultant velocity. B, use any of these as B, 23 squared plus 42 squared minus 2 times 23 times 42 into cos 54. You can solve it like this. And that would also result in the correct answer. Any questions as far as this is concerned? $34.02. So the actual answer, thank you for solving this, Ali Ahmed. Saved my time, 34.02, which is equal to 34 meters per second. Our answer is 33 meters per second. Whenever you do it using a scale diagram, they'll always give you a range. The range in this case is 34 plus minus 1. So any value between 33 and 35 is acceptable. And we got exactly 33. This is 34. That's the actual answer. Use any. I'll move on now. The engine of the aircraft in B stops. The aircraft then glides towards the ground with a constant velocity at an angle theta to the horizontal, as illustrated in figure 3.2. The aircraft has a weight of 46 newtons and travels a distance of 280 meters from the point X, from this point, to point Y. The change in gravitational potential energy of the aircraft for its movement from X to Y is 6,100 joules. Assume that there is no wind. Calculate the angle theta. Now, when the aircraft moves from X to Y, the change in gravitational potential energy happens due to this. The change in gravitational potential energy occurs due to this change in height. If I ask you, this is 280, this is theta, what is h? You know that h is equals to 280 sine theta. Or because this is the component away from the angle, or you may use sine theta is equals to opposite h upon 280. Opposite upon hypotenuse, h is equals to 280 sine theta. Now, change in gravitational potential energy is equals to mgh. The change in gravitational potential energy is 6,100 joules. The mass, I don't know the mass, but I do know what mg is. Mass times the gravitational field strength, which is 46 times h. What is h? H is 280 sine theta, and solve for theta. Or you may use this to find the height first and then plug that over here to get theta. You may do it in 2 steps, or you may do it like this. Your call. You'll get the value for theta, which is equals to 28 degrees. Yes. Moving on to part 2 of the session. Calculate the magnitude of the force acting on the aircraft due to air resistance. What is the magnitude of the force acting on the aircraft due to air resistance? Now, this is a good question. What do we have here? We have the change in gravitational potential energy. We have 280 meters as the 280 meters as the distance moved in this direction. What else have they given us? It glides towards the ground with a constant velocity at an angle theta to the horizontal. If I ask you, what happens to this change in gravitational potential energy? This gravitational potential energy, what form of energy does it get converted into as the aircraft glides downwards, as it loses height? Kinetic and thermal. Now, if you think of it as kinetic or kinetic and thermal, there's no way that you can solve this part. Why? You missed out a point here. The question says the aircraft then glides downwards towards the ground with a constant velocity, which basically means that the kinetic energy does not increase. So gravitational potential energy does not get converted into kinetic energy because the velocity is constant. So gravitational potential energy gets converted into work done gravitational potential energy gets converted into work done against a resistance, not into kinetic energy. What is the gravitational potential energy? 6,100 joule. Change in gravitational potential energy. Change in gravitational potential energy. If it's constant velocity, won't the acceleration be zero? Yes, the acceleration will be zero. You're right. We never said that the acceleration is non-zero. What is the work done against air resistance? The work done against air resistance can be written as force into distance. Force into distance. Just a second. Sorry about that. So work done against air resistance is force into distance. Why not F minus R is equals to MA? I'll tell you why not. So 6,100 joules is equals to force. What force are we talking about? We're talking about air resistance. If the aircraft is moving in this direction, the air resistance would also be in this direction, as in the direction of this plane. So that is the force. And the distance, what is the distance moved in this direction? The distance moved in this direction is 280 meters. 280 meters. So F is equals to 6,100 divided by 280, which gives us a value of 22 newtons rounded off to two significant figures. Now, Afnan's question is, why can't we use F minus R is equals to MA when we know that the acceleration is zero? We can use that, Afnan. You can. The only thing that you need to understand is what is F here and what is R here. So for this aircraft, you've got a weight over here. You've got weight acting downwards, W. And you've got air resistance acting in the opposite direction to its movement. So something like this. Here we go. Air. I can't equate this W with this air resistance, F air. Let's call this F air, the force due to air resistance. What I'll have to do is I'll have to use the component of weight down the slope. The component of weight down the slope. And we know this is equal to W sine theta. Because this is theta, the component down the slope from our classes, I hope you remember, it's W sine theta. Because it has no acceleration, W sine theta should be equal to air resistance, the force due to air resistance. Use that. If that makes sense to you, use that. W sine theta is equals to F air. Can somebody solve this? What is the weight? The weight is 46. Sine, what is the value for theta? 28 is equals to the force due to air resistance. This should also be equal to 22. 22, approximately equal to 22 newtons. So you do it this way, or you do it using the other technique. You'll get the same answer. Let's move on to question part D. The aircraft in C travels from X to Y in a time of 14 seconds. Figure 3.3 shows that as the aircraft travels from X to Y, it moves directly towards an observer who's standing on the ground. The aircraft emits sound as it travels from X to Y. The observer hears the sound of frequency 450 Hertz. This way is only applicable if acceleration is zero. No. What I did was, Afnan, I'll go back to this question. W sine theta minus F air is equals to MA. If you have the value for acceleration, use that value for acceleration. You can do it that way. Our value of acceleration was zero. So W sine theta minus the force due to the air resistance is equals to zero, or W sine theta is equals to F air, force due to air resistance. Is this clear now? So even if it was non-zero, you would get an answer. Obviously, you'd have to plug in MA and solve it. But in that case, you'd need the value for acceleration. The speed of the sound in air is 340 meters per second. Calculate the frequency of the sound emitted by the aircraft. So there are a few things here. They've given you this value of time, 14 seconds. So it covers a total distance of 280 meters in 14 seconds. What can we find out using distance and time? We can find out the speed. The speed is distance upon time, 280 upon 14, which is equal to 20 meters per second. Now, this is a question on Doppler effect. Observed frequency is equals to V upon V minus Vs times Fs. This here is Vs. Observed frequency is 450 Hertz. The speed of sound is 340 upon 340 minus 20 times Fs, which is 450. Sorry. Fs is the unknown source frequency. F naught is 450. This is what they wanted us to find out. Make Fs the subject of the equation, and you'll get the source frequency, which would obviously be less than this value. Because when a sound source is traveling towards you, the observed frequency is greater than the actual frequency, 423.529. Rounded off to two significant figures, it's 420 Hertz. Question number 4. This is a question on electric field, not part of the syllabus anymore. Good. Question number 5 then. Question 5 says, for a progressive wave on a stretched string, state what is meant by the amplitude. What is meant by the amplitude of a progressive wave? It is the maximum displacement from the mean position. Maximum displacement of a point of a particle from the mean displacement, from the mean position, is known as amplitude. Part B says, light from a laser has a wavelength of 690 nanometers in a vacuum. Calculate the time period of the light wave. They've given you the wavelength. They've said that it's a light from a laser, which means that you should know the speed. It's the speed of light. Use the formula V is equals to F lambda, where F is equals to 1 upon T. So V is equals to lambda upon T. What is the speed? 3 into 10 to the power 8. What is the wavelength? 619 nanometers, 10 raised to the power minus 9 upon the time period. The time period is an unknown. Solve for T. 2.3 into 10 raised to the power minus 15 seconds. Part C says, a two-source interference experiment uses the arrangement shown in figure 5.1. Light from a laser is incident normally on a double slit. A screen is parallel to the double slit. Interference fringes are seen on the screen at distance d from the double slit. The separation of the centers of the slit is a. The light has a wavelength lambda. The separation x of the centers of the adjacent fringes is measured for different values of distance d. So what they've done here is you get fringes on the screen when you perform this double slit experiment. And that follows the formula x is equals to lambda d over a, with this distance between two fringes is x. They've changed values of d, and for the for the different values of d, they've measured different values of x's. And we know as d increases, x increases. So this is the graph. As d increases, obviously x increases. The gradient of the graph is g. Determine an expression in terms of g and lambda for the separation a of the slits. Now, the first thing that you should know is that x is equals to lambda d over a. What do we have on the y-axis? We've got x on the y-axis. What do we have on the x-axis? We've got d on the x-axis. So what is the gradient of this graph? The gradient of the graph can be expressed in two ways. The gradient of the graph can be expressed in two ways. One method is you say, this is my y-axis, this is my x-axis. So the gradient of the graph, g, as they've used, y is equals to mx, g, the gradient of the graph is equals to lambda over a. So a is equals to lambda over g. They wanted an expression in terms of g and lambda for a. We've given them that. This is the best way to do it. Linearize. Compare it with the general equation, y is equals to mx plus c. Or you may do it using this technique, which is basically somewhat similar, lambda d over a. You may say that gradient is y over x. Change in y upon change in x. This is our y, this is our x. Y over x is x upon d. Y over x, which is equals to lambda over a. This here is our gradient. You'll get the same answer. Gradient is equals to lambda over a. So a is equals to lambda over g. Part 2 of this question says, the experiment is repeated with the slits of separation 2a. The slit separation is doubled. The wavelength of the light is unchanged. On figure 5.2, sketch a graph to show the result of this experiment. Now, a here is part of the gradient. Gradient is lambda over a. If I double a, can someone tell me what happens to the gradient? It halves perfectly. If you double a, it halves. This is like me saying, there's an equation y is equals to 3x. And then there's an equation y is equals to 6x. What will be the difference between the two graphs, the two lines? You'd say the gradient of this one is 3, the gradient of this one is 6. This one would have twice the gradient. This would be 2 times steeper. So we're doing the same thing here. When the denominator over here is doubled, This causes the gradient to become half the original value. So the only thing that changes here is that the gradient changes. And the gradient becomes exactly half. So by the end of our original graph, this one was up till this point. This one was up till this point. If the gradient becomes half, what happens? This point, instead of being this, the line, the end point of the line, instead of being at this point, this would be over here. So you will draw a line with half the gradient. The y value is half for the same x value, which basically means that the gradient is half. Afnan, what do you mean by double the line? If this is what you mean, you are correct. The gradient becomes half. This is a line with half the gradient. If the question set says, what happens if the slit separation is half A? If the slit separation is half A, the gradient becomes double because the denominator is half. When the gradient becomes doubled, you'll draw a line that goes all the way up till this point, 2 times this height. The gradient becomes double. This one is half the steepness. This one has twice the steepness of this line. That's question number 5. Moving on to the last question. I believe, yes, question number 6. Question number 6. A resistance wire of uniform cross-sectional area 3.3 into 10 raised to the power minus 7 meters squared and a length of 2 meters is made of a metal of resistivity 5 into 10 raised to the power minus 7 ohm meter. Show that the resistance of the wire is 3 ohms. Use the formula for resistance and resistivity. The formula is R is equal to rho L over A. The resistance is equal to resistivity times the length upon the cross-sectional area. The resistivity is 3.3 into 10 raised to the power minus 7. That's the cross-sectional area. My bad. The resistivity is 5 into 10 raised to the power minus 7. The length is 2 meters. The cross-sectional area is 3.3 into 10 raised to the power minus 7. Plug this in the calculator and you'll get your value of resistance, which is exactly equal to, let's see, 3.030303, 3.0303 recurring decimal, which is equals to 3.0 ohms. Part B says, the end of the resistance wire in A are connected to the terminals XY in the circuit shown in figure 6.1. The cell has an EMF of 1.5 volts and internal resistance R. The potential difference between X and Y is 1.2. So if they've told you that the potential difference over here is 1.2 volts, which means that this is the terminal potential difference of this battery. A battery with an EMF of 1.5 volts is actually providing 1.2 volts to the external load. There's a drop of 0.3 volts inside the battery. This is known as lost volts. Okay, we'll see if they ask you that. Calculate the current in the circuit. Now, for this wire, you have the resistance, you have the potential difference. You need to find out the current. You'll say V is equals to IR, V is equals to IR, V is equals to 1.2, current is an unknown, the resistance is 3. The answer comes out to be 0.4 amps. Part 2, the internal resistance R. Now, we've already solved most of it. We've already we have already marked that the lost volts inside are 0.3. We've already found out that the current in the circuit is 0.4 amperes. So the current inside the internal resistance is also 0.4 amperes. So what do we need to do? We need to use V is equals to IR once again. V in this case is 1.5 minus 1.2, like we did above. 1.5 minus 1.2, which is equals to 0.3. I is 0.4 times R. 0.3 is equals to 0.4 R. What is the answer? 0.3 divided by 0.4, which is equals to 0.75 ohms. Part C says, a galvanometer and a cell of EMF E with negligible internal resistance are connected to the circuit in B as shown. The resistance wire between X and Y has a length of 2 meters. The galvanometer has a reading of 0 when the connection P is adjusted so that the length XP is equals to 1.4 meters. And this total length is 2 meters. 2 meters, sorry, just let me. Determine the EMF E of the cell. Now, this part here, the top part is the same circuit as this one. They've just added the bottom part here, which has a battery and a galvanometer. I know that this wire XY experienced 1.2 volts. So the total wire, which has a length of 2 meters. So 2 meters of the wire experienced a potential difference of 1.2 volts. Because this wire was uniform, which means that equal intervals or equal lengths of the wire would experience equal potential differences. There'll be a constant increase in potential difference as the length of the wire increases. That means 1.4 meters would experience some EMF, and that EMF would be equal to E, the EMF of this battery. Why? Because this is the point at which it's balanced. So the potential difference across this point, across this length XP, should be equal to the EMF E. It's simple ratios. Cross multiply, solve for E. As Ali said, the answer is equal to 0.84 volts. 0.84 volts. Last part, part D. The circuit in figure 6.2 is modified by replacing the original resistance wire with a second resistance wire. The second wire has the same length as the original wire and is made of the same metal. So what do we have here? Original wire replaced with the second wire, same length, same metal. Length is same metal, that basically means resistivity is same. The second wire has a smaller cross-sectional area. The area of the second wire is smaller. Connection P is adjusted on the second wire so that the galvanometer has a reading of 0. State and explain whether the length XP for the second wire is shorter, longer, or same as the length XP for the original wire when the galvanometer reading is 0. Now, let's see what this does. What does this change do to our resistance of the wire? R is equal to rho L over A. Resistivity is constant because same metal. Length is constant because they've said same length. The area has decreased. So when the area decreases, R is proportional to 1 upon A. When the area decreases, the resistance increases because they're inversely proportional. So I'll say the second wire, yes, Madhya, the second wire has a larger resistance because smaller area. Okay. So because the second wire has a larger resistance, the drop across that total wire would also be greater. It has a greater resistance, so it will experience a greater potential drop. For the first case, for this case, the potential drop across this 2 meters was 1.2 volts. For the second wire, the potential difference across this would be, let's say it's 1.4 volt. It will be greater. Why? Because the resistance is greater. So by ratio, it would have experienced a greater potential drop. I'll say potential drop or potential difference across the second wire is greater. Now, for the same battery, the EMF of the battery is 0.84. 0.84 volts. That is fixed. We found that out. Will it be balanced at the same length? Or will it be balanced at a shorter length? Now, some of you may be confused. How do we figure that out? The thing is, you assume a value. So I assumed 1.4. You may assume 1.3. You may assume any value. So 1.4 volts. In fact, let's not use 1.4 volts. Let's use 1.35 because this is also 1.4 meter. There's a probability, there's a chance that you may get confused between the two. Let's say this is 1.35 volts. So this entire 2 meter experiences 1.35 volts. What is the length? That is gives us 0.84, 0.84, which is the EMF of the battery, 0.84 volts. Cross multiply and get an answer. Check whether it's less than 1.4 or if it's greater than 1.4. So 2 times 0.84 divided by 1.35, I get 1.244. X is equals to 1.244, which basically means that the length XP for the second wire is shorter. The length XP for the second wire is shorter. That is the conclusion. Is this clear? Any questions that you may have regarding this part? So I didn't understand the part before this. Which part? This one here? This? Afnan? Yes.